Good morning, everybody, and welcome to the Powder Cleanse online demonstration day. Obviously, in normal times, you would have all been welcome to MTC to see the equipment live, but the times that we're in mean that we're unable to do that. Hopefully, today's online demonstration will serve to give you a good insight into what the project has achieved. And I think going forward, should anybody wish to come and see the equipment in smaller numbers, then we will try our very best to facilitate that. I don't see any reason why that can't happen. My name's Tim Beaver, and I'll be presenting the first part of today's webinar on the powder cleanse technology, which has been developed by a collaboration or a collaborative consortium of 5 companies led by Carpenter Additive under funding awarded by Innovate UK. And at this point, I'd just like to acknowledge the support of Innovate UK, and specifically that of our technical monitoring officer, Neil Calder, who's been nothing short of excellent in guiding the consortium to reach a successful conclusion or outcome from the project. As I say, the project is now reaching its conclusion at MTC, with data being gathered from the final trials of a working prototype system installed here at the MTC in Coventry, and as I say, is available for demonstration to interested parties. We'll just move on to some housekeeping notes. Today's event is being recorded and will be available on the MTC YouTube channel, for which a link will be issued after the event. I also believe it will be available on our LinkedIn profiles, so if you got links to those, then that's great. You are all in listening mode only during the session, and you'll get an opportunity to ask questions in a Q&A session with the panel, with representatives of all the companies involved at the end of the session. The viewing options are shown in the 3rd bullet point on this slide. And should you experience any difficulties with accessing the event, then please send an email to the address shown which is in the 4th bullet point on the slide. I'll just wait a few seconds if anybody needs to copy down that address before we move on. Okay, so today's agenda, it's partly a PowerPoint presentation, and there are 2 demonstration videos. The presenters are, for the main part, myself, Adam Hall from Malvern Panalytical, and Owen Larkin, who will present the results of the project. We hope to give some background to the project, an overview of the system, and hold a discussion towards the end of the session in order that anybody with any questions can get those answered. So, Powder Cleanse, the project partners. Project was made up of 5 partners. 3 partners, Carpenter Additive, Farley Green and Malvern Panalytical, are effectively the commercial exploiters of the results, and were integral in the development of the powder cleanse technology in terms of powder recycling, management, and process data gathering and analysis, which you can see represented in the circles, which come together to give you the powder cleanse technology. There was a 4th partner, Aigletech, who undertook a body of work in X-ray analysis of purposely contaminated powder samples in order to benchmark the system and ourselves at MTC, who ran a series of lab-scale tests, system design support, production system analysis, and finally assembly and testing of the prototype system. You can see from the slide that the technology is an integration of those three main elements. So small consortium, but nevertheless a very hard-working one. So let's start with some facts around AM manufacturing. So firstly, the quality and cleanliness of metal powder used in AM can directly affect, or does directly affect, the process productivity and part integrity, which is true to state specific or very critically for high value components. Historically, the main focus in R&D activities have been on the development of AM machines, which has resulted in the non-optimized powder recycling processes being developed. And finally, the current generation of AM machines use powder handling equipment that do give risk to powder traceability and quality. And there are issues around exposure of powder to the environment and, of course, non-optimized or optimal equipment. The basics challenge facing the AM industry are further demonstrated here by listing the issues against key areas connected with AM manufacture. The consortium was assembled to meet these challenges, and the technology has been developed with these issues in mind, either by utilising current systems commercially available from our industrial partners, or by developing and integrating new innovative technology. So if we take a look at the basic flow for AM processes, hopefully we demonstrate that on this slide. And this is a standard AM process, and sketching it out like this enables consideration to be given to the areas of risk which are, areas of risk to a high quality process and subsequent products. Here we show the areas of risk which consist of traceability, contamination, the risk with the biggest impact, and exposure. The slide demonstrates that there are 20 instances within a standard AM process that the process could effectively fail, which of course results in massive costs to AM producers. Project progression, we commenced the project in April 2017, and it contained 9 distinct phases, from market intelligence through design and lab testing to system builds, integration and system testing. And the first half of the project was supported with the input of an industrial advisory board to ensure that the requirements of industry were heard and at the forefront of the system design. The project ran for longer than we originally intended, so we had a couple of extensions, but well worthwhile, because we all believe we've got a very good end result. So if we look at the powder cleanse system, here we see the main risks shown on the right hand side of the slide that we're trying to mitigate against. The system hardware is also shown, consisting of a powder hopper, which you can see on the right hand side, the sieving system in the center, and the second hopper for the recycled powder on the left. And here we show the system with its digital integration. Unused powder from the manufacturing process is collected from the AM machine in a storage hopper. This hopper is a standard 120 litre powder trace hopper from Carpenter Additive. Depending on the density of the metal powder, this will be approximately 450 kilograms of product. This represents a significant material value, but the used powder may no longer be suitable for reuse in high-spec parts without reconditioning. The powder trace hoppers provide an an inert storage environment that is monitored using a powderized sensor to log temperature, humidity, pressure, and oxygen content. In order to recondition the powder and allow it to be reused, it is first pneumatically transported to the Finer Green Sievegen 04 automated sieving system. This two-stage process first fills a cyclone hopper before discharging the load through an ultrasonically enhanced sieving system to condition the powder and remove any residue oversized particles that were generated during the AM process. Oversized material was collected and weighed in the oversized collection vessel, whilst sieved powder is passed through Malvern Panalytical's Institech laser diffraction particle sizing instrument. A full particle size distribution is obtained for all material passing through the Institech before it is pneumatically conveyed to the collection system. The collection system comprises of a third-party cyclone to separate the powder from the pneumatic flow. The inert gas is recycled whilst powder is collected in a second powder trace hopper. The reconditioned hopper can now be confidently reused in the high specification AM process, recovering some of the initial value of the material. As well as physically reconditioning the used powder, the system also allows traceability of the powder's heritage and pedigree. Instrumentation within the POWDERCLEANSE system collects critical environmental and material data and allows this to be linked to batch records via RFID or barcode tagging of the powder trace hoppers. The POWDERCLEANSE data can then be linked to Carpenter Additive's PowderSolve secure cloud database. This allows the entire history of the powder to be linked to the batch records and the parts it was ultimately used to manufacture. In addition to traceability, the captured data can be combined and analysed with other data sets and used to monitor, control, and improve the overall manufacturing process. The POWDERCLEANSE project has also gone further, and the feasibility of adding an analytical data with the inclusion of elemental X-ray analysis has formed an important part of the project. So if we move on to the system overview, before we move on to an online demo, the final element of the system is the overarching supervisory control, data acquisition for the system, or commonly known as SCADA. For the prototype solution, the overall SCADA system is configured using Malvern Panalytical's proprietary automation platform, Malvern Link. The Malvern Link configuration fulfills three main functions for the overall system. Firstly, and not surprisingly, Malvern Link provides the interface to the Institech particle size analyzer. However, it also handles the control interfaces to all of the other system components, including the Modbus TCP or IP connections to the Sievegen and pneumatic flow controllers, as well as the digital inputs from the hopper location sensors. The second key function is to provide the overall sequence control. Malvern Link achieves this by using pre-configured standard operating procedures, or SOPs, that are selected by the user to initiate and execute the control sequence. When the clearing sequence is completed, the final function is to consolidate the measurement data with the material and hopper references. When this is complete, Malvern Link interfaces with the PowderSolve database and publishes the results. We'll now showcase a video demonstrating the system, which will be followed by a presentation of the results by my colleague, Owen Larkin.
I will now go through the results we have obtained as a part of this project. So one of the first activities we performed as a part of this project was a simulation of an AM facility using discrete event simulation. This was primarily focused on looking at machine utilization during the AM process. The inputs into the simulation were varied, including the number and shift pattern of operators and the number of AM machines inside the facility. The process flow was created based on the processes used at the National Centre of Additive Manufacturing at the MTC. Next slide, please. The first simulation that was performed was just a simple baseline simulation. So this was based on one operator using one machine that produced one part and using powder at risk as soon as it was available, and the simulation was over 3 years. So you can see on the bottom graph, which is build chamber utilization, that only 60% of the time is actually spent building, and over a third of the time the machine is sitting idle waiting for the operator, as this is probably outside of their 8-hour shift. The auxiliary equipment utilization is shown in the bar chart above, and the whitish grey is waiting for powder. So you can see that almost all the time the auxiliary equipment is not being used, and in fact more time is spent waiting for a technician to use it rather than actually being used. Next slide, please. The next simulation performed was of a more production style environment, and there were 2 changes here. So there was an unlimited amount of technicians within the simulation, and they worked a 2-shift pattern. And you can see on the bottom graph there that the AM machine build chamber utilization has massively increased up to around 95%. And looking at the auxiliary equipment utilization, there is now much less time spent waiting for the technician, and the utilization has increased slightly. This was repeated using a larger AM machine that could produce 4 parts per build cycle. Utilization was slightly decreased to around 94%, but this is massively offset by producing 4 times as many parts for each build cycle. Next slide, please. The final simulations that were performed were looking at multi-machine setups. So here the number of AM machines was varied from 1, 2, 4, 8, 16 and 32 machines, but the amount of auxiliary equipment used remained constant for each simulation. So despite not increasing the amount of auxiliary equipment, you can see that up to around 16 machines there is very little blockage, and the only major blockage occurred when using 32 large machines serviced by one set of equipment. So you can see that also there is virtually no time spent waiting for powder. So despite the small amount of auxiliary equipment to service these machines, there is still always powder available. Sorry about that. So this shows that the sieving and auxiliary equipment, the use of them is not a rate limiting step within the process. Instead, the building is by far the rate limiting step. So that even though the sieve will require a reduced throughput in order to operate with the Intertech, this will not affect the overall process output rate. Next slide, please. So on that throughput optimization, so the Intertech uses laser diffraction in order to measure the particle size. So if too much powder is flowing through the system, it can blind it, leading to inaccurate, or in some cases, no size measurement being recorded. So in order to maintain the optimum flow rate, the output from the sieve must be controlled. Initially, this was done by limiting the sieve stack motor speeds and restricting the flow into the Intertech. This worked for the small batches that we were trialing, but when we tried larger batches, we found that powder was backing up and there was a risk of potential damage to the sieve stack. So in the second prototype system, flow restriction was added above the sieve stack instead. This had the same effects, so it limited the flow to the optimum rate, but there's no risk now of powder backing up and damaging the sieve. So even though the powder cleanse system will be slower than just a normal sieve, you then do have the benefit of having near 100% batch testing with the results being reduced in real time. Next slide, please. So in order to validate the system, the results obtained using the Intertech on the powder cleanse system were compared to results using offline testing. So powder was run through the system with the results obtained using the Intertech, and then this powder was sampled and tested using the Malvern Mastersizer 3000. The graphs show the results from both systems overlaid on top of each other, and you can see that they generally overlap, with the Intertech results, which are the yellow ones, measuring powder over a slightly larger size and recording slightly more fines. So when this results were found, Malvern undertook further investigation, looking at different powder samples and comparing the Intertech and Mastersizer, and the results observed were similar, and it is hypothesized that the differences between the results are mainly due to the different dispersion methods. So Mastersizer uses wet dispersion, and the Intertech uses dry dispersion, and the slightly different optical geometries of the sensors in both pieces of equipment. So these results showed that the Intertech produces similar results to the Mastersizer, but you also have the advantage of testing near 100% of the batch as it flows through the machine in real time. We will now show a demonstration of the digital integration of the system, which is presented by Adam Hall of Malvern Panalytical.
For the demonstration, I've established a remote desktop connection to the system's overall industrial system PC. In the prototype system, this PC will be located in an electrical enclosure alongside the system, allowing users to remotely log in as I have here. The interface shown here is the Malvern Link runtime user interface, and I've launched the Project Pacific Powder Cleanse configuration. The prominent mimic view is Project Pacific and represents the system as I've described, but also displays live status information that is of use to the user. The other item to note is the panel on the left that shows the standard operating procedure that is currently selected and the operating status of that SOP. To run this demonstration, a second instance of Malvern Link is running. This is a separate configuration that simulates the automation sensors and pneumatic flow controllers, as well as emulating the automation interface and the operation of the Sievegen 4. The final simulated item in the demonstration is the Intertech particle size analyzer. Running the instrument in simulation allows realistic measurement data to be generated. After the system is started up and the initialization sequence is complete, the user is able to start a cleaning sequence. In this demo, there is just a single user SOP, although it is conceivable that different SOPs could be selected depending on the particular reconditioning requirements of different materials or processes. To start the SOP, the user first selects the required SOP and loads it into the SOP pane. Details of the steps within the selected SOP can be viewed in the SOP Studio window. In this SOP, a series of sub-SOPs or subroutines are called that control the stages of the overall reconditioning sequence. As we progress through these sub-SOPs, we will be able to track the automation steps in this window or the SOP pane. To start the SOP, the user simply clicks Start. The initial stages of the SOP ensure the positioning and identification of the collection hopper and feed hopper. In a production system, the hopper IDs could be reliably obtained by barcode scanning or RFID tagging, but for now, these are entered manually. Next, an Intertech background measurement is taken. This involves automatically taking a measure of the optical light scattering without any product flowing through the instrument. These background measurement values are used in an actual measurement to cancel out any trace contamination from previous measurements. The process is akin to tearing or zeroing a weighing system before weighing an item. The system is now ready to start transferring the first sub-batch of powder from the feed hopper to Sievegen's cyclone hopper. The cyclone motor runs, generating vacuum and drawing product from the feed hopper. This continues until the cyclone's hopper high-level sensor is made. After the cyclone motor turns off, stopping the powder transfer, sieving of the first sub-batch is started. With a configurable combination of mechanical and ultrasonic sieving, powder is conditioned by passing it through the sieving screens. Oversized material is collected and weighed in the oversized collection vessel, while in-specification material is pneumatically conveyed through the Insutex measuring cell and then finally to the collection system. While the Insutec is running, the live measurement data is being generated and displayed here. The status of the pneumatic flows that purge the instrument's windows to prevent contamination are also shown and monitored along with the flow used to convey and disperse powder through the Insutec. As the capacity of the feed hopper is greater than that of Sievegen's cyclone hopper, it is likely that several cycles of the cleaning sequence are required to condition the entire contents of the feed hopper. In this simulation, the trigger for processing another cleaning cycle is via a user prompt, although it is envisaged that this will be automated by monitoring the hopper weight or interrogating the PowderSolve database for the logged contents of the feed hopper. For the purpose of this demonstration, we are only going to run one sub-batch. To complete the sequence, a data set comprising of the averaged particle size distribution and other system measurements is consolidated for each sub-batch that was processed. These data sets, one for each sub-batch, can then be published to the PowderSolve cloud database where they can be tagged to both the hopper and material batch. The simulation uses a manual trigger for this export, but the upload will be automatic, providing the batch has been completed successfully. Although the PowderSolve database will provide the richest source of data, it is possible to quickly verify the sub-batch data within Malvern Link using the batch tools. Here, it is possible to quickly search through records and verify data from the process. The sequence is now complete and ready to process another hopper of used material. And this concludes the demonstration.
Okay, so it's me in real life now. So it's Adam Hall from Malvern Panalytical. I've been involved in coordinating powder cleanse efforts from Malvern Panalytical's point of view. So we open up the panel now for questions. There's a Q&A button at the bottom of your screen. If you want to submit any questions on that, please feel free to do so. So while we're waiting for anything to come in, thank you to Tim, and thank you to Owen, and thank you to Owen's dog. That was good input from all, and nothing in as yet. We have had a few questions submitted in advance, so maybe if I just take one of those to start with, and this is a good one because it involves, I think, most of the parties involved. What is the maximum capacity of Sievegen by volume? And then that feeds into what is the flow rate in kilograms per hour? So I think it's one we might want to pass around a little bit. So maybe if we could go to Farley Green first of all. What is the maximum capacity of the Sievegen?
Okay, so I can take this one. The maximum capacity of SGO4S is 25 litres worth of powder holding capacity, and then this is processed through the sieving station and down into the Intertech. So in terms of this by volume, it essentially pulses 25 litre batches. As for the flow rates through the system, obviously this is highly dependent on your powder and the mesh aperture that you're actually using. But as an average, I would say the process is approximately 75 kilos an hour, which can go up to, we've seen in excess of 300 kilos an hour in terms of the sieving station itself. However, Owen did mention during the presentation that with the Intertech, the feed of powder must be a little lower to be able to get the higher results coming out here. So Adam, do you want to advise in relation to the Intertech capabilities?
Yeah, so the flow through the Intertech, it's an optical measuring system, and it is possible to put too much powder through and blind the system. We have tried to organize the flow such that we get as near as 100% of the material flowing through the system as possible, which is reduce the overall flow rate, but gives us close to 100% inspection of particles going through. It is an optical system at the end of the day, and if you block all of the light going through it, you don't get enough information to make any conclusions. So yeah, we've reduced the flow, but we have a higher inspection rate. And of course, as Owen mentioned earlier, there is plenty of time available for the processing of material, and not necessarily we can use that time to get a higher inspection rate. Anything you'd like to add to that, Owen?
Just that in some of the trials we've performed, we've got throughput rates that have been successfully measured around 50 to 60 kilograms an hour. So it's not that much slower than the speeds Charlie was mentioning before anyway.
Yeah, good point. Of course, we're as we do more trials and tests on this, we'll be able to establish some true specifications. But yeah, getting the system together and operating has been our thrust at the moment. Okay. So the other part of that question, taking it to a logical conclusion, we are presenting the powder trace hoppers at the start, and they actually determine, I guess, the overall capacity of the system. Do you want to mention anything on the hoppers, Graham?
Yeah, thanks, Adam. So these hoppers are 120 litres in capacity, and they've been designed with a repose angle to assist with flow going through to your pneumatic pipework. And that 120 litres depends on the alloy that you have. So stainless steel, nickel alloys, general density or kind of packing density of powders around 4.5. And you're hitting about 450 kilos if you were to work in from a mass perspective. But from titanium, it's a much lighter material. So you're looking at 650 to 700 kilos there in 120 litre. That's a high value powder. It's a very high value material, and it's very expensive if you get it wrong. So the purpose of this powder cleanse system is to be completely closed loop, and to protect the powder and to protect all of the operators from exposure to that powder.
Okay, very good. Thank you, Graham. And we've got a panelist question in. So thank you, Neil. In processing recovered powder from typical AM builds, what is the ratio of passed to rejected powder? Right, anybody want to take that one? Is that anything we've covered in our studies, Owen?
Not specifically in this, but we will be able to get data from our AM team, but I don't have it on me at the moment. That is one we will be able to answer.
Okay.
So I would just like to add on to that one, Adam. Passed to rejected powder is normally a function of reuse. So as you're reusing your powder multiple times, very unlikely that you will have just your virgin material. It's very expensive to start with. you put it in your machine once. You may build parts that could be 10 kilos, but you need 50 kilos of powder to even build the 10 kilos in the first place. That leaves 40 kilos left over. You need to use that powder. You need to utilize it as best possible. If you know your powder is good, you put it back in your machine, which is the whole point of having a closed loop inline inspection system. I don't have an exact number on the pass to rejection rate, but I do know as you recycle powder, the powder does degrade over time. So that's something to be conscious of, and that's an investigation that we can support in.
Yeah, and of course that ratio probably depends on the final application of the parts that you're looking to build. Different applications will have different requirements, aren't they?
That's correct. Yeah, every application has its own specification, and every part has its own material specification, or at least every alloy will have its own material specification, whether it be compliance to an aerospace standard, an ASTM, or even an automotive or medical. There are different specs all requiring different requirements. So it really is application dependent. Yeah.
And I guess that's one of the things that we've seen coming out of this project is that these standards are still very very early in their lives, and we can see them developing and evolving even over the course of this project. Okay, so nothing else from attendees.
Adam, there's a question from Robin Weston saying, what action does the system take if the powder analysis suggests a problem part way through the cycle?
Yes, got it now. Very good. What actions? So that's probably one to me. I think that's a little bit to be decided at the moment. We can detect problems as they occur. There's several actions that are possible. You can either stop the whole process and investigate, which you may want to do for a highly critical application, or because we're running in sub batches, you may want to just reject that sub batch, so that the entire hopper would be very expensive to disregard, but you might want to just disregard part of it, or maybe put that through for processing again. So I think how you actually use the system is going to be very application user specific, and it might be that you can, because you've got the traceability history of a particular batch, you might be able to. It might not be good for aerospace, but it may be useful for a general build. So I think we can tailor the system to do what is required. It's how you want to make use of the data, but yes, we can stop it. Okay. Anybody want to add anything to that one?
Yeah, Adam, I'd just like to just point out that I guess the sub batch analysis will give you your results in real time through the Marvin Link software, and also through having the visibility of your particle size. I'd say that you don't really know if your material is out of spec on size until it's gone through your Incitec and until it's actually being conveyed into the hopper. Being able to reject that is certainly one option, but really understanding what the root cause is and doing a bit of problem solving and actually understanding, is that really a rejection or is that just a one-off sample? However, the bulk sample of your entire batch of powder is actually in spec. So it's very easy to say, oh, it's slightly out of spec by 1 micron. Let's reject everything. Actually, what is really happening in the system?
Yeah, so the more nuanced approach may be that it gives you an option to quarantine a batch or a sub batch rather than necessarily reject. But again, I think that's down to particular applications and what the final part's going to be used for. Okay, so more questions coming in. which MC platform is this system currently compatible with? So which machine platforms is this currently compatible with? So, well, we're using it as a standalone at the moment. Anybody want to pick that one up?
I can make a brief comment on this one, Adam, just to kind of kick us off, really. We designed this entire system to be machine agnostic. So the machine input from the hose, from the input of the Sievegen, could be from the hopper, could be directly from the machine. If you have an external output in that machine, whether it be a DN25 adapter or a KF40, something like that, we have adapters to then fit into each machine as long as there's a machine output.
Indeed, and just to add to that as well, in terms of it's not just on the internet side that this is as compatibility, it's also in the returning of powder as well. So earlier on, we showed a infographic which demonstrated the system essentially attached up to an inlet hopper and an outlet hopper, essentially. But they could quite easily be replaced with other systems without too much effort.
Absolutely. Okay. Very good. Right. So another comment in here. Who's coming on the chat? Will the equipment be accessible to third parties for evaluation after the project? One for you, Tim, is that?
That can be discussed. At the moment, the equipment is accessible for demonstration, and evidently we would, if an evaluation was desired, we would try our best to work towards that. So quite possible, I would say yes.
Yeah. Okay. And of course, we've got the project formally comes to a close at the end of the month, isn't it? But
yeah, so the project finishes officially at the end of December. There's no budget for evaluation on behalf of third parties, but we can certainly, on our part, from MTC's part, we would inquire with our relevant peers to try and facilitate such an event.
So if anybody does want to look at it in real life, please get in touch and we can see what we can do.
I think it's important to say that this project has taken us to TRL or TR level 6, and we're looking to take this further, but that would actually require a project, a real life project to take it on board.
Yeah, so the technology demonstrator is TRL 6, so technology readiness level 6, looking at a demonstratable prototype in what's it called, a real world scenario, I think is the definition. So yes, it's working, it's actually performing, but like the questions on rejects and quarantining, that is detail that we can still work on and build into a real solution. Okay, so I think that's starting to dry up. One last chance. So I think I'll bring that to a conclusion. Any final comments from the panelists before I think we're going back to Graham next, aren't we?
So there was just one comment from me that the idea of the powder cleanse system as well is that it could be customized, for some of these application or requirements. So we've got a prototype at the moment, but again, that can evolve a little bit depending on the requirements of an end user.
Yeah, good point, John.
Yeah, I think it's a really good point, that, because although we've got this system, it is a mechanical and a digital integrated system. It will add value to a facility once we do a full facility integration, and that will require some bespoke integration. whether it be to hoppers, to machines, or even optimizing your powder processing layout. That's certainly all options that we can discuss.
Okay, thanks guys. So we'll hand it over to Graham now for some closing remarks.
Thank you for that, Tim.
Just before you speak, Graham, on the bottom of that slide are the email addresses for Graham at Carpenter Additive, David Buckley at Farley Green, and Adam at Malvern Panalytical. Should anybody wish to get in contact, please do. Please ask away. That's what we're here for. Sorry, Graham. On you go.
No, that's fine. That's a really good introduction. And thank you to everyone that attended our remote demonstration today. As we've all said, especially Tim, in different times, we would have invited everyone to the MTC and had a real demonstration and being able to actually look at the remote connection and how versatile it is. We all hope that you found this information really insightful and thought-provoking. I wonder, for anyone that's in the panel, that's in the audience as well, how many of you are actually tracking your material reuse or waiting for sample results? And how many are operating in a closed loop system to improve your user safety and avoid unnecessary build failures through contamination? So they're just some open questions, really. The powder cleanse system has been a great example of a collaboration between technology experts in the field of AM. And we've developed a digital integrated system, and we've set out on this goal for the past 4 years, and we've achieved this goal to TRL level 6. We can now optimize and validate your material reuse process, which is a huge tick in the AM industry. So I'd like to thank the Innovate UK team for supporting in the development of this project, and our project monitoring officer, Neil Calder, for the ongoing support and direction for all the QRMs and all the random phone calls I've given. Thank you to all the partners in this project. So Carpenter Additive, Manufacturing Technology Centre, Malvern Panalytical, Farley Green, and Eagle Tech. I just like to, just one last word, really, your commitment and perseverance through the development barriers we've had to face during this project is nothing but inspiring. So thank you very much, team.